Today is the last lecture. I want to briefly speak about two things. Well, first, so we have shown that for the FK model at Ising parameter, the interface converges to SLE 16/3. So I want to speak briefly about how one can use this to reduce this to the loop soups and such. So can one get not just one interface, but whole soup of interfaces? So this is fairly recent work with Antti Kemppainen, and so I don't want to get into the all details. But basically, what we had, so we proved that we do this loop FK model. So in the loop FK model, so it's with partition function sum of square root of q in power number of loops, and we take q equal 2. We have shown that interface converges to SLE 16/3. So the setup was that we have a domain, and then we have a picture which goes something roughly like that, and then this interface is SLE 16/3. So naturally there are many more things here. So there are loops. It can have a picture, for example, something like that. So there'll be different loops, which I just get with different colors. So what one can show that, which is not quite written yet, that this whole soup of loops converges to CLE with parameter 16/3, and that's, I think, CLE, Wendelin briefly spoke about what is CLE, the collection of loops, each of which is individual CLE. So what I will sort of indicate how to prove is that one can, so sort of this is a theorem which is half written and half being written with Antti Kemppainen. So this is 15/16. And this basically theorem says that we can write so this collection of loops can be rewritten as a branching tree. So I will say in a second how you do this. And this branching tree converges when mesh goes to 0 to a tree of SLE 16/3, 16/3 minus 6. So that's again something which Wendelin must have mentioned as SLE kappa rho. So it's SLE with a drift, and minus 6 drift, it means that you don't see where you're going. So let's first me describe the discrete case. So suppose we want to use these loops to get from A to B, and well, then we just go from A to B along this curve, no problem whatsoever. Now suppose that we pick another point, let's say for example Z, and suppose that so what is a branching tree? So the tree. So let us define, so we define a branch which goes from A to Z. So how do we define it? Well, let me maybe put Z first, not here, but here, that would work better. So suppose we want to go to Z using this system of loops, and well, again, we put some ant or a bug on a lattice, and he'll start walking. So if he walks along this curve from A to B, so far he does not know whether he will get to Z or not. So for example, it can very well be that point Z is somewhere here, and then just we'll hit it, and that's it. That's the branch we want. So just so the first step is walk from A to B along the interface, So if we hit Z, then we just stop. That's the branch. Now, if we don't hit Z, which is the case here, so when do we realize that we don't hit Z? We actually realize it not at B, we realize it a bit later. In this picture, when you reach here and you turn to the right, you realize that you no longer can hit Z because Z in a different component of connectivity. So we are now walking, at this point we hit the boundary, we split our thing into two parts, and we are exploring the wrong part. So it means that we are going along the long branch of a tree, so we should step back and we should jump here to this cycle. So if we hit Z, no. If we don't hit Z, if we never hit Z, if otherwise, we take last time we were in the same component as Z, jump to another cycle. So this basically the picture for the first one was that we just go and we hit Z, and then we stop. The picture for the second one was that we somehow go, and our branch goes further, but Z is in this component, so Z somewhere here. So what we do, we go, and at this moment when we disconnect Z, we don't go further, but we jump instead, and we continue going with the same parity, so we just make 90-degree turn on a different loop. And we just, we remember that we jumped a loop, so there is a point where we jumped a loop. Is it sort of okay? I mean, it's what is nice about this picture, if you do the same on hexagonal lattice when there are loops, there is no really canonical procedure or logical thing which comes to mind, but here it's sort of basically the unique thing. So if you explored your configuration up to here, still there are configurations which are the same up to here, but where you hit Z. So again, since we want to keep the Markov property, we can decide when we jump only using our path of our curve. So what we do here, we reach the point when if we make step to the where only one step leads to Z, and then we, if our interface turns left, then we just follow it. If it turns right, then we jump to a different cycle. So let's go here along this cycle. And again, here we reach a point where we have to jump to get to Z, so we jump and we go, and we hit Z. So basically, so this is the algorithm. And then we return to the first point. So walk along interface. So we start at A. So when we do this jumping procedure, we jump onto a loop, but we immediately cut this loop at one point, so it becomes an interface which starts at a point and ends at a point. So essentially what we do graphically is that we walk along this thing. When we reached here in this picture, there is another loop attached. So we cut this loop at this point, and we now have this sort of new domain. So new domain looks like that, and new domain has an interface which starts at a point and ends at the same point. So actually, most likely it will be very small because it's conditioned to start and begin and end at the same point. But then next time we jump, we have another interface, which also most likely will be very small. But once in a while, we'll get long ones. So this is basically the procedure. So the result is that for every z there is this sort of itinerary which is uniquely defined and which is composed of parts of loops. Okay, is it? Now the very important observation. So it's let's say I can't put it as a lemma, but it's too easy. So observation. Suppose we take two different points, z and, for example, z prime. Or maybe let's do z prime here. So let's see what happens with z and z prime. So I'll put z prime in a different color. So first we go. At this point we still can reach z prime, but we jumped to z away, and the thing for z prime, it just goes. That's the last time when we make round turn. So we jump here, we go around. Again, that's the last time when we can still reach z prime. So we jump and we reach z prime. So basically, if you have two different branches to z and z prime, so what happens is that first you follow the same path, and then these two branches, they diverge, like on this picture. So essentially, if you take any 2 points, the branches up to some moment coincide, but then they split. And when they split, one goes into one domain and another goes to another domain. So if you are you and your friend are driving to different destinations, first you follow the same highway, but at the moment when you part, you actually exist in different domains which are disjoint and completely independent. So two branches coincide up to the moment when they become completely independent and live in disjoint domains. So branch from A to Z coincides with branch from A to Z prime until the time when Z and Z prime are disconnected. And after this time, then these branches are independent. Naturally, because they just live in two different domains. Yes?
About the definition of the branch, I'm probably misunderstanding something. So I cannot see why you would always obtain a branch from A to Z, because, for example, what if Z is not on an interface?
But that's exactly this example. So this is, for example, this Z is not on the interface. It's on a loop. But we get a branch because we follow the interface until the time it can still hit Z. Here it cannot. Then we jump to a loop.
Yeah.
We follow, yes?
Is the loop an interface of some clusters in the FKEs?
Oh, no. But I mean, our picture of loop is like fully packed. So these loops, they cover the whole plane. Yeah. So that was what I was sort of saying, this stupid remark that if you do loop representation of O of n mod on hexagonal lattice, they don't cover the whole plane. So there are some free points, and then there is some ambiguity how you would define a tree to get to this point. So it's not, I don't know a good definition. One can still define it, ending some randomness, how you jump or how you walk in if there are no loops. But here, like, loops cover everything. So Z lies on some loop. So essentially what I'm saying, that if you have a collection of loops, you can then take scissors and glue. So you cut each loop at one place, and you glue it to another loop, and then you get a tree. And there is a canonical way to do it, just using this exploration. So basically, the sort of lemma is that if you start with a collection of loops plus point A, in principle you can start collection where there is no interface. You can start, for example, with collection something like that, and just start with cutting this loop at point A and exploring from here. And then there is a unique way to cut loops and make it a tree. And here, here we hit this loop and we attach it. Here we hit this loop and we attach it. And here we hit that loop and we attach it. So collection of loops becomes a tree. And basically what you do, you cut every loop, glue to another. And I think that sort of the best way to do it is indeed that you draw a branch from, for every z you draw a branch from A to Z, and then the union of these branches will be exactly this tree. It will tell you how to cut. So basically, the way here is that you draw interface from A to B, and each time it disconnects a part of our domain, you glue the last cycle you visited there. Then you go along it, you draw it, each time it disconnects, you glue the last cycle you visited. So it's not that last time you visit a cycle, you glue it. No. If you still can enter this domain, you still continue. But last time you visit some domain, you glue it. So if you draw the thing from A to B, it splits it into some number of domains. In this picture too, but on a big picture it would be 1,000. And for each of these domains, you take the last time you visit, and you glue the cycle you visited last. And then you continue this by induction, so each of this cycle splits its own domain into a few components. Last time you visit each, you glue it, and you get this tree.
Why is it going to be tree?
Why it is going to be a tree? Well, because it's going to be a tree because each cycle, when we attach, we cut it by scissors. So basically we had this thing from A to B. So this is last time we visited some cycle. So we cut it here, so it is a branch. Then it has cycles attached, so it looks like that. So it's each cycle is cut, so it's not it's a tree because each cycle we cut at one place. Well, I mean, it's simply connected, it won't have any loops. If it doesn't have any loops, then it is a, well, any graph which doesn't have any loops and is connected is a tree. So it's connected because we can reach, every point can be reached, because every point is on some cycle. It's a tree because it doesn't have any loop, because we cut all the loops with scissors. So it's connected because we took a tube of glue, and it's not a tree, it's a tree, it has no loops because we took scissors. So it's the two essential elements here. But it's the thing which I like on this picture. Well, you can draw a picture and then just look. It's sort of canonical, as I'm saying. If you have these models where loops are not dense, one can also try to construct SLEs, but I don't. So, for example, if you take picture of Ising, which has SLE 3, theoretically it should have a tree of SLE 3 minus 6. But I don't know a nice way how to draw it on a picture, on discrete picture. I don't know how to draw a nice discrete counterpart of it. And the reason why I cannot is, well, because it's more difficult than this case, and it's more difficult because in the Ising you would have loops, but you can have, for example, a big C of plus spins. And the question is how you draw the tree on this big C of plus spins. And it should be essentially a percolation type model where you just toss a coin each time you reach some place, you toss a coin where they go left and right. So here, the tree here, you get deterministically from the picture of loops. In this picture, you should also add some randomness when you have a lot of plus spins. And this translates into some statement about these two SLEs, how they behave, which will eventually appear in a paper of Werner, Sheffield, and Miller, I think. yeah. So it's which is being written. Okay. So this is the construction of a tree. Okay. Now this observation. So yeah. So it's the correct observation that it's a tree. But also the observation is I want to reiterate. It's the same observation as before, bless you. But I want to reiterate it. So it says essentially that you don't see where you're going until you hit it. So you don't see the target point until you hit it. So, for example, if you have two branches to two nearby points z and z prime, they will coincide to the very last moment, and they will branch like one step away. If you have z and z prime which are a little bit further away, still you reach their neighborhood, then you disconnect them, and then you branch. So it's very much like, in Ising model, for example, here, our boundary conditions are such that we know we have to have point B to define the curve from A to B, or in spin Ising model. But in percolation, when we do the percolation interface, we don't have to do the other point because boundary conditions we don't need. So if you do this percolation interface, so what we are doing, we were covering this in yellow and this in blue, just sort of for convenience. But we can cover otherwise with a different target point, and you would have that you just go the interface and it's they will coincide until these 2 points are disconnected. So SLE6 for percolation, it has this property built in that you don't know where you're going. And it's the only SLE which has locality property. And SLE 16/3 doesn't have this property built in. But it arises here. So the question is, how can it possibly arise? And the answer is that it arises with SLE kappa rho. So the theorem is that branch from A to Z converges to SLE 16/3 minus 6, which is minus 2/3. What is different? Why you get a SLE kappa rho? Well, look, in our picture, now there are 3 points, A, B, and Z. So before there were only 2. So when we uniformize to a plane, then we uniformize, so Z goes to infinity, A goes to 0, so we have this SLE from 0 to infinity. But we also have a point B, somewhere here, well, let's say U, and B goes to U. Because it changes the boundary conditions, so if we try to build a continuous model very much like SLE, we immediately notice that it's not a half plane with 0 and infinity, but there is also one marked point. So the usual SLE, when there was no marked point, there is a driving force, which is a Brownian motion, and you don't have much choice, only the speed. But when you have a marked point, you no longer have this sort of stretch invariance. So it means that you can have some diffusion which depends on the position of this point. So it can be Brownian motion with some drift, and indeed it is. Now, how much Werner said about the SLE kappa rho? Did he say a few words, or?
There was one exercise session, but on the lectures there was actually nothing.
Nothing. Ah, nothing. Okay, yeah. Nothing. So essentially, well, okay. Let me just write an exercise. Well, no, I don't want to write an exercise. So it's maybe I will. So what is a good way to introduce it?
So it was introduced with this group of SDEs in the exercise session.
Can we just write a martingale?
Yeah. That's exactly what I'm going to do. But then you know, never differentiate in public. I will pull out my notes or my. Oh my God. Yeah, I forgot my notes at home. Okay, but I have a copy of my old slides, so it's not that bad. Yeah, so it's... Okay, so it's just since I always get the notation, so I just want, well, I can do it without the notes, I just want to use the same notation as people always use. So there is this saying that in analysis you are not allowed to change the notation, because if you change notation, you denote U by V, then still once in a while you sleep and write U, and then it will all collapse eventually. Okay, so basically, okay. So let me how to do it. So let me. So what did I do so far? So I defined this branching tree, and I explained that two branches, they coincide until the time they go into different domains, so they're completely independent. So what is clear from that if we describe one branch, we'll be able to describe the full tree, because branches are coupled in a very easy and nice way. So they coincide until some time tau, and then they're completely independent. So if we describe every branch individually, most likely there would be much energy needed to describe the whole tree, because they are coupled in the most straightforward way. They coincide until they go to different domains, and they are completely independent. So there is this. So the picture, I mean the picture of this, well, which is like that. If you draw it with time, it would be a picture that there is this branch. So it goes like this, sort of. It's fairly common in probability to study branching processes. So for example, you can study Brownian motion, which at some points branches into two Brownian motions. Or, I mean, there are coalescing Brownian motions where you start several Brownian motions, when they hit each other, they glue to each other. And if you run it backwards, you will get a picture like that. So here, the difference is that what we have actually this tree embedded into the plane. But if we run it, if we start studying it as a linear revolution, and we draw the driving forces of these branches when they're described by linear revolution, it will be exactly like branching Brownian motions, that there is a Brownian motion, and this time it branches, but the two things, they describe to linear revolution in two independent domains, so they don't care about each other at all. So it's really at each of these points. So at this point, we split our domain in two, and of course, the two halves are completely independent. In this time, we split the first half in two, and so on. So the question is, can we describe individual branch? And the proof for this theorem, sort of a proof for an individual branch. So I don't want to speak about how the branches, how you pass from individual branch to all the branches, because as I'm saying, that is not difficult. It's sort of on hand-waving level, it's clear that they are coupled in a nice way. So it's only a matter of finding reasonable words to explain why it happens like that. So you should really sort of find some words how you describe this point where you branch in continuous setting. So in continuous setting, essentially, it would be more or less the same thing, that you draw your continuous curve facility and it splits domain in two. But then you should also check that discrete setting converges to continuous setting, that you don't get any fake branching points, so every branching point there becomes a branching point in the continuous, and that you need a priori estimate, and that gets, so it's sort of straightforward what you should do, but it's technical and at times demanding. But that's sort of the moral there is here. So, but for individual branch, again, you need to find an observable. And what do we need? We need to find an observable. So we had an observable f with a and b from point U. Now what we need, f, a, b, z, from point U, because we have one more marked point, and we have somehow to incorporate it into our whole scheme of things. So we need some observable which describes this picture. And the observable actually is not even, the correct thing is not even with 3 marked points, but with 4. Let's say Z1, Z2. Because how can I possibly mark this point on a picture? Well, I can mark it with scissor. Well, I can mark it with a pen, but then it's not very visible. So the best thing is to mark it with the scissors, that you split this cycle and you get 2 sources very much like A and B. And these are Z1 and Z2. So what we do, we cut an edge at Z, and we get two sources, Z1 and Z2. So 2 edges which stick out. So here there were 2 sources, A and B, and now we have actually 4 sources, Z1, Z2, A and B. So there are 2 possible scenarios of this thing. So one, when Z is on the boundary, then you get 2 sources on the boundary. If Z is inside, for example here, then you get 2 sources inside. So in continuous setting, the first thing is that you mark 4 points, but 2 of them are basically the same. And the second thing is that you mark a point inside. So I will discuss this case, which only gives us the branches which go to the boundary. So it doesn't give us branches which go to interior points. But the other case, in some sense it's easier, in some sense it's more complicated. It's more complicated because it took us a few more years to do it, because it's slightly more difficult to find a correct function f here. On the other hand, it's easier because here you need to be able to work with fractal boundaries, and when you are inside, you are not fractal because you are inside domain, everything is flat, and when there is fractal, you don't care because it's far away. So the first thing, so what you have basically the very same thing we had before, but with the 4 marked points, which in principle you can take Z1 and Z2 apart. Now, so it's a 4 sources, so sort of to say, let me just indeed draw some picture. So, for example, something like, well, this is an example of a legitimate domain where it's A, Z1, Z2, B, and I even made it more general, so I put Z1 and Z2 apart. So we know how to do an observable with 2 sources. So how do we, what is the most straightforward thing to do with this one? The most straightforward thing is to kill 2 sources by just joining them by an edge. So what you can do, you can, for example, take Z1 and Z2 and join them by an edge. Or you can take Z2 and B and join them by an edge. So what you do, you join Z2 and B, and what you get then, you have this domain which has 2 sources, and then there is this very long edge which connects these 2 points. And if you do the usual proof we had about function f, everything can be transferred here. F will be analytic inside, everything is fine. The only thing which happens with f that you remember when we were discussing h, we have a function, let's say f1, we have a function h2, h1, which is harmonic homomorphic, and H1 is, so it's F1 is basically square root of gradient of H1, and H1 is basically, well, integral of imaginary part of F1 squared. So now the only thing is that before, in the usual time, we had that H is equal 1 here, H is equal 0 here. And we were getting it by saying that H jumps at these 2 points. And H jumps at these 2 points because well, there is the interface always goes between them. So here, H will have 4 different jumps. It will also jump at this point because there is a positive probability that you go, well, there is a positive probability that the picture goes like that, and then H will jump at this point because the interface will go through this thing. And on the other hand, there is a possibility that you have a picture of loop. So, well, this is our loop picture. It has a bunch of loops also. And there are basically 2 scenarios. If you have 4 sources, either they can be joined horizontally or they can be joined vertically. And in the first case, this is my interface for which the function f is defined. And in the second case, this is my interface for which function f is defined. So you always have a jump at these 2 points in both cases, but at these 2 points you have the jump only in the first scenario. So basically what you have there is that the function h1, it jumps, and its jumps are of size 1 at these 2 points, and of some unknown size, what are the good letters we never used before, like say r and r. So this is and basically if you say that probability in the original model, there are probability of this picture we denote by, let's say, P1, and probability of that picture we denote by P2, and of course P1 plus P2 is equal to 1 because it's sum of probabilities. What we'll be able to say about these jumps? So we have jump in the station 1, but not in the station 2. So what are the sizes of the jumps? So the tempting thing to say is P1, because this picture is P1 and this picture is P2. But it's slightly more subtle, because if partition functions without this additional h are proportional to P1 and P2, with the additional h, here you get an additional loop. So it's P2 square root of 2. So basically, partition, or let's say partition functions here are P1, P2, or probabilities, let's say partition. So the partition function of the same thing with this added edge, in the first case it's still P1 because you just added edge not to a loop, but in the second case you create one more loop, so it's P2 square root of 2. So the jump actually will be, jumps will be equal to P1 divided by P1 plus P2 square root of 2. And if you stop here, you are in a bit of a pickle, because a priori you don't know P1 or P2, and you got a function f up to one parameter which you don't know. So that is a small problem. On the other hand, we can do the same function but with a different edge. Then we similarly join what is it? We was Z2 and B, join Z1 and Z2, and then we get function F2, function H2. So it's exactly the same picture, but we have these two things joined. And if these two things are joined, then it's the other way around. Here the partition function is P1 square root of 2 because we created one more loop. And in the second picture, the partition function is P2. So the jumps in the second picture will be slightly different. So you always have jumps here and here. You have jumps 1, 1, S, S. And S will be equal to P2 divided by P1, square root of 2 plus P2. And what I don't have time to speak of is that you get these two functions and you know them up to parameter P1, but now there are two of them and you can play with them, and apparently you can write a difference of those two functions so that P1 doesn't participate in it at all. And then you can calculate it, and then a posteriori you get the value of P1. So basically, maybe I don't want, because the calculation gets rather nasty. Well, no, actually it doesn't get rather nasty. Yeah, so it's maybe yeah, actually no, it's not that bad. Yeah, maybe I'll write what is going on. So it's so what you can do, you can write the difference. So we have so write the difference f1 times something minus f2 times something, so that one jump disappears. So one function had jumps which were what? 1, 1. So one function had jumps 1, 1, S, S, as being P2 over P1 plus square root of 2, P2. And the other function had jumps 1, 1, R, R, and R being P1 over P1 square root of 2 plus P2. So if we write, for example, so suppose we want to kill this jump. So what you write then, you write S, well, you write R, so this is F1, this is F2. You write R F1 minus S F2, and this new function, well, let's say F, it will have jumps, so here it will have RS minus S, so RS minus S. Here it will have jump R minus S. Here it will have jump R minus RS. And here it will have jump 0. Yes. Yeah, and better yet, you multiply it, you divide it by R minus S, because then the jumps will be, one of the jumps will be equal to 1. Okay, so this thing still looks scary enough, because I promised you to get rid of P2 and P1, but if you plug in, you don't get rid of P2 and P1. They're still all over the place, because R and S are some linear combinations, so we have some funny linear combinations here. But let's before we think about unpleasant things, let's first try to think what happens with the function f or function h. So you remember when we had function h which had jumps 1 and 1, well, basically it's 1 and minus 1, we had a map, we had h having values 0 and 1 and map to a strip. Now, if we start writing values of h, for example, h equals 0 here, h equals 1 here, and then it jumps, and here it does not jump. So what I claim is that you can check that in this case, you get a map again to a strip. So these two parts are two opposite ends of the strip. And this interval, it has some other value of h, let's say h equal to alpha. And it's mapped to a cut in a strip, and this point is mapped exactly to the tip of this cut, which one can show with argument principle and with conformal maps, so that what we know that h is equal to 0 here, it jumps by 1, it's equal to 1, and we know that it's equal to some constant. So we know that the morally picture is something like that. But why it is exactly conformal map? Because it turns out that you can check from analyzing f1 and f2 that the boundary conditions here, the derivative is positive. Here derivative is negative. So this one looks up, this one looks down, this interval. And here on these two you have the same value alpha, but up to this point you look down. And after this point, you look up. So it's exactly where you go around this point. So essentially, what you can say about function h, if you just know 0 here, 1 here, and constant there, you can say that function h, if you write it as imaginary part of analytic function, it's an analytic function which sends this arc to this line, the other arc to the other line, and the other arc to somewhere here. But if we know that the normal derivative is negative and then positive, it will actually be forced to send it around half line. So it's a little bit like, you remember how we reasoned why this is a conformal map by argument principle, because when I go from here to here, I travel on this line. When I go from here to here, I travel on this line, and then I'm forced to walk exactly once around every point. So here you can do a similar argument for every point on the strip which is not at height of alpha, that when you go around, you walk exactly once around this point. And so you can deduce that it's a map to such a picture. So it's a conformal map. And now, basically, conclusion is that h is imaginary part of phi, where phi is a conformal phi from omega with 4 boundary points marked, conformal map to a slit strip. But depending at which height I draw this line, I will have different conformal modulus. So conformal modulus, for example, between these two arcs, is the same as here conformal modulus between this line and the bottom of this half line. When I change the height, the conformal modulus will change. So there is exactly one height alpha for which you will have this conformal modulus. And even let me maybe just write, if I'm at it, so this we can map to a half plane which has 3 points marked in infinity. And if I want to map this to a half strip, then basically what should I do? I should do a function h which has no jump here, but jumps at 0 and 1. So what has jump at a point 0? Logarithm z has jump. So you remember when we were writing, so this thing where 0 goes to end, it's given by log z. And the thing where 1 goes to one end, it's given by log z minus 1. And here we have to have a combination of these two, so it's a combination of two logarithms. And the combination of two logarithms I must have written somewhere. I just look it up. So it's a combination of two logarithms, and the combination of two logarithms is, so it's actually u log z plus 1 minus u log z minus 1. And this height will be 1 minus u times pi, and the total height is pi. So essentially we get in the end something like that, 1 over u times pi divided by pi. So this jump is equal to the jump we have here, r minus rs over r minus s. And then we can write p1, we can write p1 in terms of u. So if it's all confusing, I want to go through it again, and basically the steps are the following. So we have, with 4 marked points, we have 2 possibilities to connect them. First possibility or second, which they have partition functions p1, p2, and or probabilities p1, p2. So one parameter, the ratio of this p1, p2, which we don't know yet. Now we can add an extra edge in 2 different ways. Well, there are actually 4 different ways, but they're linearly dependent. There are only 2 interesting ones. And this gives us 2 functions, f1 and f2, which are not yet known because they have jumps depending on relative probabilities. But we can take combination of these 2 functions, which eliminates 1 jump. So it eliminates 1 jump. Still, we don't know what it is because the other jump is written in terms of p1, p2 by complicated formula. You have to plug in s and r into this formula, so you get some bigger fraction. But one can argue that this function f and h, it's actually h is given by a conformal map. And if h is given by a conformal map, there is only one possible choice of the height of the slit, which is just dependent on conformal modulus of your 4 points. So what you do, you have your 4 points, there is a conformal modulus, which you just calculate by mapping to half plane, and this is parameter u. But with the parameter u, you then uniquely can write such a map. There is only one conformal map, and it's this combination. Well, for different values of u, you just get different moduli, but it's this combination. So in this case, you know it not by calculating p1, but you know it by arguing that it's conformal map, like in the original case. This gives you parameter u, and this a posteriori gives you this equation on p1, p2, which is a huge equation, but then you can solve it, and I don't remember, it's actually, I think, miraculously, you even get a nice answer. Yeah, so let me maybe write. So if one opens so all the brackets here, you actually get some formula which is not that bad. p1 squared times p1 plus square root of 2p2 squared over p1 squared plus square root of 2p1 p2 plus p2 squared. So it's fairly mild as the things go. And then the other way around, you can get that you can solve this the other way around. So p1 plus p2, they give 1 as a sum, so you can plug in, well, use that p2 is 1 minus p1. So you can actually solve for p1, and it turns out that, well, at first glance it seems to be a degree 4 equation, but it's actually, you can take square root, so it's a quadratic equation, and the solution is not bad. So it's just some number. Okay. So what is the conclusion of all this before we go to the break? So first of all, we calculated, as a byproduct, we calculated relative probabilities of these 2 pictures. Now, these 2 pictures, if you write them in the language of the FK model, you have 2 arcs which are wired, and you have, well, and then there are a bunch of clusters, and then there are two arcs which are dual wired. And you have a probability of having a connection here. So actually, this is like Russo-Seymour-Welsh for FK model, with particular boundary conditions, wired, dual wired, wired, dual wired. But this gives you access to Russo-Seymour-Welsh. You can then try to do more difficult boundary conditions, but even that is enough for most estimates. So as a byproduct, we got a priori estimates like for percolation. So we got that probability of this connection only depends on conformal modulus of this thing, which means that for same shape, it will be the same in the limit. But also we got this coefficient, so the conclusion is what we have. We have Russo-Seymour-Welsh type estimates. So we can do all the a priori estimates which I cheated and didn't do. We can just deduce it from today's lecture. But also we can now we can do the two functions I wrote first. F1, F2 are okay. And it turns out that the function F1 is actually a martingale with respect to this tree. So if you are, no, the function F2. So if I want to build the tree to the point Z, and I do Z1, Z2 here, so if I do a function which joins them by a small arc, this function is martingale with respect to a tree branch. It's very easy to check when you just wander here, because it's just the same thing as usual. But then, no, wait a second, what I'm saying? No, I'm saying wrong thing. It's a martingale if you join these 2 points. Yeah, it's a martingale if you join these 2 points. Yeah. Again, I don't want to get into the details because we ran over time already. But let's say, and so let's say function F2, which you obtain by adding h like that, is a martingale with respect to the branch. And the reason is that as long as you don't jump cycles, it's martingale as usual. But when you jump cycles, each time when you jump cycle, what happens is that when, for example, you jump from a cycle to another cycle, what happens is that you, at this point, you basically erase the cycle which goes through A and B. And you lose a factor of square root of 2. And it turns out to be exactly what you need to do if you explore the branch, that each time you jump a cycle, with scissors, you cut one cycle, so you should lose square root of 2. And this is done by these boundary conditions. So you then go on this cycle, and then there is this AB. So these boundary conditions are sort of logical, because if you jumped on some cycle, what you did, you cut it with scissors, but you should sort of remember that it was a cycle. So this is what this thing does. So, okay, so basically what I explained today with some proofs and some absence of proofs, that using exactly the same technique and a little bit knowledge of conformal maps, we can construct a martingale for a branch. The only thing which is different is that, of course, it's a more difficult martingale because it's a map to a strip with a slit. And then we actually have to take a limit of this map when 2 points collapse. So it's a more difficult formula than before. So it's just a more difficult formula than before. And I'm not going to finish it before the end of the lecture. So what I'm going to do after the lecture, I'm just going to write what this martingale is, if we would have done it. And what are the conclusions about the driving SLE. So let's maybe take a break. Okay, so maybe the two important things of this part of the lecture is first this tree, which is a nice combinatorial construction. And the other thing is that sometimes to determine what is your unknown analytic function, you can use it as a conformal map from argument principle or something else. But the main thing is the tree. Okay, so the tree. So let's have a 10-minute break, and then I will continue. So we describe a branch of a tree by Löwner evolution. Now, since we have 3 points now, basically we do that, we draw from 0 to infinity, and then there is point B, which is for the boundary condition. So the usual normalization is that, well, let's say, so we have this half plane, and we started drawing our curve, and so I will just write everything in half plane, and we normalize it by a map GC, which is z minus ut plus twice t over z plus small order terms at infinity. Well, there is this marked point. So we say that it's normalized, so t goes to 0, and the marked point goes to vt minus ut. Why people write vt minus ut? Because you can also write the map G, you can write map gt plus ut, which is z plus twice t over z plus so on at infinity. And then in this case, the tip goes to point ut, and the marked point goes to vt. So let's say I will draw a circle around the marked point. So a small remark is that if our curve goes like that, like on this picture, then the mark point just stays here. But you can also have a picture where your curve touches and surrounds the marked point. Then from the observer at infinity, the marked point at this moment will jump to the point where you have touched. And then you continue from this point, and mark point stays here. And if you again surround it, it will jump again. So the marked point is viewed from infinity, and if you surround it, then it will jump to the place where you surrounded it. It very much corresponds to our branching thing. So in our branching thing, if you remember, there is a marked point B, which is the end of this interface. But when we touch here and jump to a new thing, the B jumps here because we cut this cycle, and the new B is the other end of this cycle. So it's a B prime. So it's exactly the same thing. So we always view the marked point from infinity, well, or from point Z, which is our target. And then whenever we do this collapse of a domain, marked point moves to the point where we collapsed, which is quite logical because just before we collapsed, the observer sees it exactly in this place, because the light rays in conformal geometry, they will go through this field. So this is just one thing to understand, that in Euclidean geometry it might jump once in a while, but in conformal geometry it's always in the same place, so you always see it in the same place. So it's like faraway star which moves continuously, but in reality it might jump galaxy away. Okay, now what are the usual formulas which we write here? So the usual thing which are written is that, well, Vt, just as usual. So what is the usual? What is the usual Löwner equation? dgt is 2 over gt minus ut dt. So that's the usual Lovni revolution. So this is the usual Lovni revolution. And SLE, you just write that ut is square root of kappa bt. Now in our setting we have to write two formulas for ut and vt. So let's write two formulas. So the vt formula is very easy. It's 2 over vt minus ut dt, because the point vt just flows under the Lovner flow like all other points. So if it's inside, which we didn't work out, then it's normal flows. It's on the boundary, again flows on the boundary, but at the moment of collapses it jumps because you view it as a boundary point. So that much is easy. Now the question is what you write as a ut, and the usual thing is that people write that dvt minus ut, so you can get ut from this formula, is minus square root of kappa dbt plus, let's say, kappa d minus 1 over 2 dt over vt minus ut. Maybe, you know, maybe no. Maybe I will do it with another. Let me do it with rho plus 2. Okay. So this is called SLE kappa rho. Well, why this? Why exactly this drift and not any other? This is, you can ask Wendel and Werner because he introduced it. So essentially, well, you can write any drift in terms of Vt minus Ut. So it's logical, of course, to make it Vt minus Ut because, well, it's conformally invariant, so it should be a function of Vt minus Ut. Then there is a question how it should change when you stretch your thing under conformal multiplication by 2 and or 5 and inverse proportionality immediately comes up. That is the only reasonable thing. So it's this something times some constant. And the constant, well, people denote it by rho plus 2. That's it. So essentially this means that we have here, it's called the Bessel process. So you know Bessel process. So this is the thing is, so this is Bessel process of dimension d equal to 1 plus 2 rho plus 2 over kappa. So it's basically this coefficient tells us what, so this coefficient also can be written as kappa d minus 1 over 2. So if you factor out kappa so that it's a standard Brownian motion, then you factor out square root of kappa here, and then you get d minus 1. So Bessel process has several definitions. So for example, Bessel process of dimension t, so let's say BP dimension d, it's absolute value of Brownian motion of d-dimensional Brownian motion. So if you take Brownian motion in dimension 3 and you take its absolute value, then you will get Bessel process of dimension 3, which in our case corresponds to this being equal to 3. So Bessel process of dimensions 1 to Bessel process of dimension 1 is just the usual Brownian motion on half line. Bessel process of dimension 2 is absolute value of Brownian motion in the plane, then absolute value of Brownian motion in R3 and so on. And it's an easy exercise for stochastic calculus, so you must have seen this in stochastic calculus, that if you write it, it will be a neat diffusion where the main term is Brownian, but you will have also some drift which depends on the distance from the origin. And the drift has this coefficient d, and then of course it's quite logical to take d also non-integer. So that was mentioned in stochastic calculus Bessel process. Yes? Yes, yeah. So basically it's clear that you should get here a Bessel process. It's less clear what you would do if you have not 1 marked point but 5 marked points. If, for example, there are 5 sources. And again, Wendelin, Aded, and Greg, they have definition of a silly kappa, row 1, row 2, row 3, where every point gives you some sort of Bessel input. But then it turns out that there are logical situations. For example, you do Ising model where there are several marked points and there are boundary values plus, minus, etc. There are logical situations where if you describe Besselian interfaces, the drift is no longer Bessel, it's something more complicated. So if you have more than 1 marked point, then there is, as far as I know, there is no nice description. So Ising with 4 marked points, the thing which when 2 points haven't collapsed yet, if you described it by a silly, then you get an ugly thing. It's not a silly kappa row. So unfortunately, it's not a silly kappa row 1, row 2, so unfortunately it doesn't seem to be a logical description of drifts, which would have been very nice because you also can do this drift thing if you run a silly, for example, if you run a silly on a, say, Riemann surface, say torus, you start running a silly, then you immediately have a modulus because the torus already has a modulus. And you have torus with a whole n marked point. So you again have drifts depending on the modulus. So as far as we know, there is no, in some situations there are some reasonable, nice geometric thing. But in some we don't know whether there is a good approach. But this is more about SLE. And the hope, of course, is that to realize what works nice for SLE, you can analyze lattice model and see what works there. But for Ising with 4 boundary points, it already spoils it a little bit. It doesn't work. Okay, so there is no nice answer. Now, a very special row is played. Rho equal kappa minus 6. So the SLE kappa minus 6 is local. For example, SLE 6, 0, which is just SLE 6 because you have no drift whatsoever, is local. It means it doesn't see where it's going. So it to SLE kappa minus 6 aimed at 2 different points, say at Paris and London, until they cut the Earth into 2 different disjoint parts, they coincide exactly. And then they are completely independent. So there is one value of rho for which SLE is local. And for kappa equals 6, this rho is equal to 0. Also SLE 6 is local, so this is the percolation SLE, which doesn't see where it's going. So basically, if you know SLE, if you read papers of Ulrich Werner, went to his course and then did some reading, it's clear that our branch should be SLE 16 over 3 minus 6. Because it is SLE for FK Ising model, so 16 over 3, but it doesn't see where it's going, so it should be minus 6. So basically, kappa equal, so our case, kappa equals 16 over 3, and locality, rho is equal to 16 over 3 minus 6, so minus 2/3. So we know what we should get. But apparently one also can get it from observables. So if one calculates these observables, which I didn't have time to calculate, then one gets let me just have a look. So our observables in this setting, they give you the 2 things are martingales and 2 things, let me just so that I don't screw the formulas. Okay, so okay, here it's in 4-point case here when it's not a silly kappa rho. I have slightly different. Okay. So our observer was basically, so I can just, so after all the calculations, you get that f is square root of number h, and h is actually z plus, how to denote v minus u? Let's say v minus u, I denote by p. So z plus p over 4 logarithm 1 minus pz. So the martingale which we get is square root of gradient of this, so it's square root of gradient of z is 1 plus, so what is the derivative of logarithm? Is 1 over p over 4, 1 over 1 minus p over z. And derivative of 1 minus p over z is p over z squared. So this is the martingale. Again, one can calculate exactly what it is. And also, there is another martingale. So unfortunately, this, when you expand and you do the trick with power series, it turns out that you need 2 bits of knowledge, but 1 bit of knowledge is identically 0, so it's some coefficient vanishes. There is another martingale, which is square root of p plus minus square root of p, and this is exactly probability of this event p1. It is also a martingale. So this is from f, and this is probability of such connection, which is also a martingale. So you get 2 martingales, and in the end, what you get? So if so, let's say, well, maybe M1 is, let's say, this is M2, and M1 is from expansion of square root of delta h, and it is, so I'll just write the relevant coefficient, it's pt squared minus 8. Yeah, by plus minus square root of p, I mean that each time when we jump to a different cycle, we toss a coin whether we take square root of p now or minus square root of p. It's sort of a stupid thing, because this probability when the point collapses is equal to 0, because if such 2 points collapses, probability that you have this connection is 0. You are more likely than to have such connection. And basically, you get that square root of p is a martingale. But each time it hits 0, you should assign a random sign to it, because if you have a curve like this, which is martingale away from real line, it's not martingale when it touches, because it jumps in the positive direction. But if you do each time randomly plus minus, then it becomes martingale just from this. So it's well, okay, I don't want to get into that, but there are these 2 things which are martingales. So we have 2 martingales, square root of p and pt squared minus 8. But if it would have been p, you get a Brownian motion. But if I denote square root of p by, let's say, q, it means that q is a martingale, and q to the power 4 minus 8t are martingales. So it's not Levy's theorem. It's different from Levy's theorem, because there is a power 4. So it turns out that this essentially implies that pt is Bessel with the number we want. So it implies that PT is exactly the Bessel process which we need. So it's PT is Bessel, so it's minus square root of kappa dB plus alpha over PT dt. And the numbers are exactly what we need. So kappa is 16/3, and alpha is kappa minus 4. Well, it should be minus 4 because we have 2 here. So rho is equal to alpha minus 2 is equal to kappa minus 6. So this I don't have time to speak about. And this is an interesting thing because you don't find this theorem that it's a Bessel process in modern books on stochastic calculus, but you find in old books from earlier times. So it's so there was a student of McKean who wrote a paper where he basically proved all such theorems. So essentially, very much like for Brownian motion, two martingales are enough to determine it. For any diffusion, two martingales are enough. So the usual theorem which people quote, in which probably was mentioned in stochastic calculus class, is Struck-Varadan theorem, which tells that if you have a diffusion which is generated by this elliptic operator, here is the list of all martingales it has. And then there is a countable, well, there is a family of martingales. And inversely, if some diffusion has all this as martingales, it is exactly that diffusion. So there is a stronger form of Struck-Varadan which says that actually the first two are enough to pin down the diffusion. But for some reason in modern textbooks, usually it's not proved. But basically it's, let's say, Levy type theorem. And in this particular case, it's first time it appeared in the PhD thesis of Arbib, who was student of McKean.
What is for good enough class?
Well, it's basically for it diffusion. It's basically for it diffusions. They back then they wrote slightly differently the elliptic operators which generate. They took one derivative out of the brackets, so they did not second derivative, but first derivative of a function times first derivative of thing in question. And then you ask a little bit less. So basically, what you can do if for example we had not gone to Wendelin's course, you have never heard of a silly kappa rho. If we wrote this observer, we wondered what is the generalization of a silly, would have automatically been led that our thing is driven by some diffusion which has these two properties. And then looking through all the literature, you prove that this diffusion is a Bessel process, so we automatically have Bessel process driving the diffusion. Okay, so this gives you one branch, and then you just should work that the coupling stays the same in the limit, and this is basically a question about a priori estimates. Now, I think this is a good place to stop. I would want, I would like maybe to leave one exercise which won't be done in the exercise session. So this is how to do in the same way spin-Ising model. So that's an exercise. So I will write a sketch of proof for the spin-Ising model. So let's say the spin-Ising. So we have let's say configuration of pluses. So I have again point A, point B. And I assume that the boundary conditions are plus on one side and minus on the other. And then inside you have some configuration of pluses and minuses. So for example, something like that. No, maybe I would just. So this generates a bunch of loops. So in this particular picture, there is only one loop. No, wait a second. So what did I want to do? I wanted to, yeah, let me just do this picture. So in this picture, there is one loop which surrounds this plus. And then there is also an interface. Now, if you notice the interface, there is some ambiguity how you draw it. So these points we could have done like this, but we could also have done, for example, with the loop like that. So there is some ambiguity with interfaces. In the end, it turns out that it's not important. So the theorem is a theorem that interface, however defined, converges to SLE3. And you can take left turn always, or you can toss a coin. So basically it means that such pictures, they occur, but they are microscopic, so they don't change the global structure of the interface. You can't have such a global thing that you have to decide whether to turn left or right, and you have this big loop of size million on the left, big loop of size million on the right, and turning left or right changes your interface drastically. No, they always will be microscopic. So the observable f here is the following. So f of z. So you don't so you have to do, let me just draw, right, partition function from a to z divided by partition function from a to b. I will tell in a second what is the partition function from a to z. So partition function from a to b is the usual partition function. So it's z is sum of x to the power length of loops. And critical x is always, I always forget, it's square root of 2 minus 1 or something like that. I always forget, so I write on a piece of paper and then, okay, so there was one piece of paper in the world with the value of x and I lost it. So x, I think it's equal to, what is it, square root of 2 minus 1, x critical. I think that, yeah. So if you normalize by partition function for the usual boundary conditions, then you automatically get a martingale. That's what we discussed for loop erased random walk. So whatever you do, if you normalize by partition function, you get a martingale. So this is f is a martingale. Now, what is the thing I get in the denominator? So in the denominator, you do the following thing. You assume that your interface ends not at B, but at some point in the middle. So you assume that you have a picture like that, that you start here, you go and 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 go, and then, for example, here is Z. So Z is an edge center. And then there might be some, there might be some loops. So you forget about point B, you only leave point A, and here you see we don't write probability of some event in our model. We write instead some partition function where our model it's it's no more an Ising model, because we don't have pluses separated from minuses by interfaces, because interface adds in the middle of the model. So you can't really cover it in plus or minus. So this is what is called by physicists a disorder operator. And what we do, we say that Z of AZ is the sum of all such configurations. Of course, xc to the power length of loops. But then we take the usual thing which we did already for FK model. We take lambda, the same lambda, which is e to the power minus I pi over 4, lambda to the power number of turns from A to Z. So the same thing with the winding that, so for example, this weight is 1. This weight is minus I. This weight is minus 1, and so on. So there are a few claims. So first, this function f is well defined. Well, why well defined? Why do I ask? Because I can have a picture like this one on this board. And this picture, you can draw it differently as a collection of loops. You can draw it like that, or you can draw it like this. So what I claim that winding might change. Winding actually doesn't change on this picture, but it would change on that picture. So on that picture, you can either go like this, or you can go like that. So the winding changes. So in this case, you make 4 turns. In this case, you make minus 4 turns. So you have to check that lambda to the power minus 4 is equal to lambda to the power 4. So lambda to the power 8 is equal to 1, which is actually true. And you have to check that this is the only thing you can get, that it's defined. So f is full defined because number of turns modulo 8 is okay. Now f is discrete holomorphic with exactly the same definition as before. Now it's the same definition on the same lattice, so let me just draw a picture. You remember that in FK model we were using a slightly different lattice. We were using lattice like that. And our definition was that, for example, if I take these 2 points and values of function f at these 2 points, for these 2 points the real part coincides, for these 2 points imaginary part, for this projection on something, etc., etc. So here what we have to check is that if I take values of f on 2 nearby edges, for example this edge and this, then for this pair of points something will coincide, either real part or imaginary or something appropriate. This is basically the same bijection trick is for the Ising model. So if for example, here is, well, that's what are the good letters. So suppose that here we have A and here we have B. And we want some projection coincide. So suppose that projection on vector alpha coincides. So that would mean that A plus alpha squared A bar is equal to B plus alpha squared B bar. So if projection on one coincides, then A plus A bar is equal to B plus B bar real part. And now we just have to again draw all possible pictures. So for example, suppose we have our interface arriving here, like that. Then what we can do, we can prolong it one more step to arrive here. And if here weight was x, here, which in this case is real because there are no windings whatsoever, here the weight would be x times lambda times x small critical, because we made it one step longer and turned left. So x is real. So for this particular picture, so what we would want to do for this particular picture, we want to have this property. So this contributes to A, and this contributes to B. So we would want to have 1 plus alpha squared 1 bar is equal to lambda xc plus alpha squared lambda bar xc. And then there is a bunch of other pictures, so I'll just draw maybe one more. So suppose we have a picture which arrives like this. Then what we can do, we can redraw this last line to go right. So if this thing had weight x lambda squared, 2 left turns, this would have weight x lambda, 1 left turn, where x is real. So we would want to have a property which is lambda squared plus alpha squared lambda bar squared is equal to, what's the right? Lambda plus alpha squared lambda bar. Well, lambda bar is minus just negative power. And there are 2 more possibilities, but they give the same equations, more or less. So there are a few more possibilities, but it turns out that all equations give the same. It turns out that you can solve them in alpha, It turns out that solution is always the same. So the first one, for example, says that alpha squared is 1 minus lambda xc over lambda inverse xc minus 1. The second alpha squared is lambda squared minus lambda over lambda inverse minus lambda minus 2. So it turns out basically that, so there are more equations, that these 2 numbers coincide. So the exercise is to check that I didn't screw up the calculations. The exercise is to check that indeed for Ising model at critical temperature, I think critical temperature is this one, but you also get it from this. So it's just possible to check for which lambda and x you would get a definite alpha. And then it gives you the usual analyticity. Now, what happens with the function h? So there's the third part. And it turns out that the function h is just Poisson kernel at this point. Because you can easily check that there are no jumps on the boundary. Boundary is uniform. And the only jump which happens is at this point, because when you do this trick, you cannot do it where the curve originates. So where the curve originates, if you erase one step, you get delta measure because, so it's just like for loop erased random walk, we had a similar thing that first step produces delta measure. So, h is harmonic in the limit, and basically you get that h is a Poisson kernel. So delta measure at A. So in the language of SLE, it would mean that H is imaginary part of 1 over GT. So Poisson kernel half plane is imaginary part of 1 over Z. So the martingale which we have is square root of derivative of 1 over GT. So martingale is square root of gradient of H. So it's square root of minus gt prime over gc squared. So the first exercise was to check combinatoric. The second exercise is check that this implies SLE3. That if you take that this is a Martin-Gavin with the expansion trick, you get that kappa is equal to 3. Okay. So this is a good place to stop. Now it's an interesting area in the sense that we don't have any more theorems. I more or less told all theorems. There is one more conformal invariance result, which is about dimers, and it probably David briefly mentioned it in his talk, or didn't he? He wrote Castellane matrices, yes? He wrote it with 1 and I and minus I, or he wrote it with real coefficients? With real coefficients. So there is a Kenyon's way to look at Castellane's matrices, which gives conformal invariance there. So that's one thing we didn't discuss, but in some sense it's equivalent to what I have been doing last 20 minutes. But basically all other models are wide open, and we don't have self-awarding walk, we don't have percolation square lattice, we don't have three-state Potts model, and for some reason it works much nicer for Ising than, say, for other models. Okay, so let's. So you are welcome to do any of those results. I will be glad to see. And it's not even clear whether any of them should be incredibly difficult. There is still a possibility that some of them there is some magic which works, and it can be done. Okay, so thank you.